Hi class. In this lecture, we're going to talk about basic set concepts. So in mathematics, what a set is a set is a collection of objects or a group of objects. So we're going to talk about how you define that in mathematics and a little bit of operators on sets or operations on sets. So our objectives for this section or this lecture, there are a bunch. So the first one is we want to use three methods to represent sets. We want to define and recognize what's considered an empty set. Okay, we want to use these symbols. This looks like a weird looking E and then an E with a line through it. What these are going to stand for is if something is an element, or I'll define what an element is, or exists or is part of a set and something that's not. We want to apply set notation to sets of natural numbers. We want to determine what we call a set's cardinal number, and that's just like the number of objects in a set. We want to recognize what we call equivalent sets. We want to distinguish between finite and infinite sets, and then we want to recognize equal sets. Okay, so first off, what the heck is a set? So a set is a collection of objects whose contents can be clearly determined. So like a group or grouping of things, right? A collection or group of objects. So elements or members are the objects in a set. And a set is well defined. A set must be well defined, meaning that its contents can be clearly determined. And the order in which the elements of a set are listed are actually not important. Okay, generally when we're dealing with numbers, though, we'll put them in numerical order, but actually how they're listed is not important. Okay, so capital letters are generally used to name sets. So we'll call sets like set T or set A or set B or Z, things like that. And a word description can designate or name a set as well. Excuse me. So if we use W to represent the set of days of the week, okay, so think about what days are on the week, right? Like Monday, Tuesday, etc. We use the roster method to list the members of a set. So this is how we're going to define it. The set W is equal to, and then we get these special bracers. These type of bracers indicate that it's a set. And then we list all the days of the week, right? And like Monday is an element in the set, Tuesday is an element in the set, Wednesday is an element in the set, Thursday is in the set, Friday is in the set, Saturday and Sunday are all elements in the set. So we use these commas to separate the elements. And as I said, we use these bracers are used to designate that the enclosed elements form a set or group. So a set is just a group of common elements defined somewhere. So this is the set of the days of the week. All right, so let's write a word description for this set. So P is equal to, and then in parentheses, we have the set of the names Washington, Adam, Jefferson, Madison, and Monroe. So kind of think about like from your history class, what this is the set of. Well, this set P is the set of the first 5 presidents of the United States, right there. Okay, that's just all this is the set of. Just the collection of them, and then the elements are just the names of the first 5 presidents. All right, so let's write using this roster method. Let set C is the set of US coins with a value of less than $1. So express this set using the roster method, so the listing of them. All right, well, so the US coins are less than $1. So C is equal to, well, we have a penny, a nickel, a dime, a quarter, and a $0.50. And then we just have these bracers to represent the set, and then these commas to delineate or distinguish the different elements of the set. All right, so that's roster. We also have something called set builder notation, okay? So it looks like this. It's a little weird. Remember our first one, okay? W. All right, so W was the set of the days of the week. So the way you use set builder notation is you define the set, you call it a letter, so set W equal is, then you see this notation tells us it's the set of, we use this variable, we do not call x, so all elements x, such that, so when you see this vertical line in set notation, it means, okay, we have x. Well, what is x? X is the variable such that x is a day of the week. Okay, so we read this notation as set W is the set of all elements x, such that x is a day of the week. So it's just defining x instead of listing them all out. So instead of saying Monday, Tuesday, Wednesday, whatever, we're just saying, hey, look, we have this set. It's got these elements x, and x is defined such that it's a day of the week. That's all this is. So before the vertical line is the variable x, which generally represents an element in general, so just a general element x. And after the vertical line is the condition x must meet in order to be an element of this set. So I know, hey, x, but it's only included in this set if it meets these conditions right here. Okay, so let's let this one. So let's convert set builder to roster notation. So express set A. A is equal to an element x such that x is a month that begins with the letter M. So using roster notation. So x is a month that begins with the letter M. Well, there are only 2 months that begin with the letter M, namely March and May. So thus A is equal to the set of March and May. And that's it. So here it was in set builder notation, and here it is in roster. All right, let's talk about the empty set. Okay, so the empty set, obviously, you know what that is, just a set with nothing in it. So the empty set is also called the null set, is the set that contains no elements, so there's nothing in it. So we represent the empty set by 2 things. Either an empty set of bracers or this notation right here. And this is kind of what we refer to as the empty set, and this is the null set. It kind of helps seeing it that way. All right, these are examples of empty sets. Okay, so here's one. The set of all numbers less than 4 and greater than 10. Well, there's no numbers that are less than 4 and greater than 10 at the same time, so that would be an empty set. And the set X such that X is a fawn that speaks. So there's no fawns that speak at all. So, you know, that's an empty set or null set. All right, so let's see, which of the following are empty sets? Well, what's confusing sometimes is with the letter zero, or the number 0. Like here, this is actually the set of the number 0. So this is not an empty set. No, this is the set just containing one element, and the one element it contains is the number 0. Also here, if you just list 0, no, this is a number, this is not a set. So you have to see, going back, this to be the empty set or empty bracers here. So neither one of these are empty sets, just so we're clear. All right, so which of the following here? X such that X is a number less than 4 or greater than 10. All right, no, this set contains all numbers that are either less than 4 or greater than 10. So it could contain the numbers 3 or 11. So there's actually an infinite number of things that this could be. So you have to be careful of logically. So in the prior example, it was and here, but here it's only 4. And X such that X is a square with 3 sides. Well, yes, this is an empty set, absolutely, okay, because there are no squares with 3 sides. All right, so you can see the subtle difference here. All right, so let's talk about notations for set membership. All right, so this notation here, this funky looking E and E with a line through it. The symbol, I'll call it E, is used to indicate that an object is an element of a set. So the symbol E is used to replace the words is an element of. So when you see this, it means something is an element of this. So this symbol here is used to indicate that an object is not an element of a set. So this symbol is used to replace the words is not an element of. So, hey, this is an element in this set. So this is one of the objects in the set. And hey, this is not one of the objects in the set. Okay, so determine whether each statement is true or false. Is R an element in this set here? So A, B, C, dot, 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 all the way to Z? Well, yeah, true. R is a letter of the English alphabet. That's what this set is indicating. 7 is not an element of this set. 1, 2, 3, 4, 5. Yeah, that's true. 7 is not in here. Okay. Now, how about this? This is weird. Set A is an element in set AB. So this is actually false because this is a set. So set A is a set, and the set A is not an element in this set. So you have to be careful here. Like if this had just been A by itself, yes, A is an element of this. But this set is not an element of this set here. Okay, so you can see, just be careful of that subtle difference here. All right. So here's some other specific ones. All right, we'll talk about the set of what we call the natural numbers. So the natural numbers we'll always call the capital letter N like this, is equal to the set of 1, 2, 3, 4, 5, goes on forever. So the 3 dots or the ellipses here after the 5 indicates that there is no final element and that this list goes on and on forever. So the natural numbers goes to a million, a billion, a trillion, and so on. All right, so let's express each of these following sets using the roster method. Okay, so first one, set A is the set of natural numbers less than 5. Well, A, the natural numbers less than 5 are 1, 2, 3, 4. That's it. Set B is a set of natural numbers greater than or equal to 25. Well, natural numbers go on forever. So it would be B is equal to 25, 26, 27, 28, comma, indicates that it would go on forever, and then we'd close this. Okay, this one's weird. Set E is equal to all the elements x such that x exists or is an element of n, and at the same time, x has to be even. Well, so that would be the even natural numbers, which would be 2, 4, 6, 8, comma, goes on forever, because it would be 10, 12, 14, on and on and on. Okay. So let's talk about inequality notation in sets. So some of the inequality signs. X here is less than A, so that's just strictly less than. So x such that x is an element of the natural numbers and x is less than 4. Well, that would be just the numbers 2, 3, and 4. Here, x is less than or equal to, so when you see this line under it, it includes equal to. So x such that x exists in the natural numbers and x is less than or equal to 4. Well, when you get this underline here, that would include 4. So it would be 1, 2, 3, and 4. And then it's the same thing with x is greater than a or greater than or equal to a. So you can see the subtle difference. X such that x is an element of the natural numbers and greater than 4. Well, that would be 5, 6, 7, 8, so on. X is greater than or equal to a. So x such that x exists in the natural numbers and x is greater than or equal to 4. Well, that would be 4, 5, 6, 7, comma, so on. So you can bound it between two inequalities. This is a, x is greater than a but less than b. So if it's a natural number between 4 and 8, well, that would just be 5, 6, and 7. All right, greater than or equal to a but less than or equal to b. So if it's a natural number, 4 less than or equal to x, less than or equal to 8, well, that would now include 4 and 8. So it would be 4, 5, 6, 7, and 8. And you can have the one-sided inequalities too. So like less than or equal to a, but less than b. So less than or equal to 4, but less than 8. Well, that would be 4, 5, 6, and 7. And the same thing here. 4 is less than x, which is less than or equal to 8. Well, that would be 5, 6, 7, and it would include 8 here. All right, so let's do some. Express each of the following sets using the roster method, so listing. So the set of all x such that x is an element of the natural numbers and it's less than or equal to 100. Well, the solution here would be the numbers 1, 2, 3, 4, comma, all the way to stop at 100. Okay, because it would be less than or equal to. Here, x is such that x is an element of the natural numbers and it's less than or an x is greater than or equal to 70, but it's less than 100. Well, so it would start at 70 and go 71, 72, 73, but it wouldn't include 100 because it doesn't have the equal sign there, so it would have to stop at 99. All right, so let's talk about now what a cardinal number is. All right, so the definition of a set's cardinal number. So the cardinal number of set A is represented by, and then it has n, and then in parentheses, whatever you call the set, is the number of distinct elements in the set A. So the symbol NA is read N of A. Okay, so N of A, so the cardinal number of set A is another way of seeing this. The important thing here is repeating elements in a set neither adds new elements to the set nor changes its cardinality, so its cardinal number. All right, so find the cardinal number of the following sets. So A is the set of 7, 9, 11, and 13. So N of A, so the cardinality of set A is, well, there's 4 elements and it's 4. Remember here, set B is equal to the set of 0. So this is not the null set, remember. So the cardinality of set B, or N of B, well, there's 1 element in the set, so that's it. Here, 13, 14, 15, 16, 17, 18, 19, 20, 21, 22, 23. The cardinality of set C, or the number of elements in set C, well, there's 11 numbers here. Also, all the cardinal number does is just count the number of elements in the set. Literally, that's it. All right, so let's talk about equivalent sets now. So what the heck are equivalent sets? So set A is equivalent to set B, means that set A and set B contain the same number of elements. Okay, that's all equivalent means, just the same number of elements. So all it has to be is the cardinality of set A has to equal the cardinality of set B. Okay, the number of elements in A have to equal the number of elements in B, and then they are equivalent sets, not equal sets, equivalent sets. All right, so these are equivalent sets, okay, because each equaled 5. Set A, X, such that X is a vowel. Well, there's 5 vowels, A, E, I, O, U. And set B, such that X such that X exists as a natural number, and it's between 3 and 7. So 3, 4, 5, 6, 7. They both have a cardinality of 5. So the lines with this arrowheads indicate that each element of set A can be paired with exactly one element of set B, and the same thing with each element of set B can be paired with exactly one element of set A. So the pairing them, basically they have the same cardinality, they are equivalent sets. So one thing we talked about just with that pairing here is the one-to-one correspondence in equivalent sets. So if set A and set B can be placed in a one-to-one correspondence, okay, what that means is each element in set A can correspond to exactly one element in set B. Then A is equivalent to B. And if set A and set B cannot be placed in a one-to-one correspondence, then A is not equivalent to B. So it has to have this one-to-one correspondence to be equivalent. All right, so let's determine if some sets are equivalent. So this figure over here shows the preferred age difference in a mate in 5 selected countries, okay? So they have it for women and for men. So set A, all right, is the set of the 5 countries shown. So Zambia, Colombia, Poland, Italy, and the United States. And set B is the set of average numbers of years women in each of these countries prefer men who are older than themselves. Right? Are these sets equivalent? Okay, so here's women, 4.2, 4.5, 3.3, 3.3, 2.5. All right, so let's try the correspondence method here. So set A is the name of the 5 countries. And then if you look at set B, well, 3.3 here, you do not write 3.3 twice. Okay, so we are interested in each set's distinct elements. So you see that this Poland and Italy both go to 3.3. So the lines with arrowheads indicates that a correspondence between the sets is not one-to-one. Okay, so the elements Poland and Italy from set A are both paired with the element 3.3 from set B. So these sets are not equivalent because they do not have the same number. You can do the counting, right? So like set A has 5 distinct elements, set B has 4 distinct elements, right? So because the sets do not contain the same number of elements, they are not equivalent. Okay. So I think the counting method is just easier. Do they have the same number of elements? They're equivalent. Piece of cake. I just want to talk now about finite sets and infinite sets. So set A is a finite set if the cardinality of set A is equal to 0. All right, that is set A is the empty set. Or another way is if n of A, the cardinality is a natural number. So a number like 1, 2, 3, 4, whatever. A set B whose cardinality is not 0 or it's not a natural number is called an infinite set. All right, now let's talk about the equality of sets. Set A is equal to set B means that set A and set B contain exactly the same element, regardless of order or possible repetition of elements. So we symbolize the equality of set A and B just by using the statement A is equal to B. All right, so let's determine whether each statement is true or false. So here, the set of 4, 8, 9 is equal to this the set 8, 9, and 4. This is true. They contain the same elements. How about this one? The set 1, 3, and 5 is equal to the set 0, 1, 3, and 5. Well, this has an extra 0, so this is false. They are not equal sets. All right, that's your basic introduction to sets.